Hello everyone, welcome to the course. Today I am uploading the very first video of this whole course, which is how to develop reactive application using Vertx. So today we will mostly discuss about what is reactive programming. Okay, so this one. So here we understand how it is different from the conventional multi-threaded approach that we generally take to handle concurrency. So let's look into it. So what is reactive programming? So before we understand this particular term, let us first understand what is the conventional approach that we generally take to handle concurrency. In general, we take this multi-threaded approach. Suppose we have a single client over here, and this is our internet, and if it's sending a request to our service, say microservice, so once this request is reach this microservice, it does some call to say maybe a persistent systems like database to get some data, or maybe a cache. Okay, and then after a call from to this particular persistent systems, it returns back some data from here, and then it processes some data, and after doing the process it sends an output to the user. So this happens to be a very general flow for any request that has been sent out by the client to the backend. Okay, now suppose here we are talking about only one client. Okay, one particular client. What if this client's increases from 1 to say 1 million? What do you do? So 1 minute. So in case of multiple users, scenario changes. Okay, it doesn't stay as simple as it was for a single user case. So for example, if there are multiple users, okay, say user group, this is internet, or maybe the load balancer, you can say. Now as we sending, or as all of these users sending this request, what happened in the microservice, we end up creating multiple threads for each of the users. So if there are 4 users over here, you can see we have created 4 different threads. Say if we number those users, say this is user 1, this is user 2, user 3 and user 4. So similarly for each of these user we created separate threads to handle their request in a concurrent manner. So now for suppose say to handle or to execute one request, say the microservice takes 100 milliseconds time, okay, for one request to process. Okay, now suppose in this 100 milliseconds time frame, if say we have 10,000 requests coming, okay, 10,000 requests are coming in 100 milliseconds time. So what this microservice will do, now as for now assume that in the load balancer we have the capacity of creating only one microservice. Okay, let's not assume that we will spawn the microservice as per the number of requests are coming. Let's assume that there is only one microservice running, and that's the maximum number of instances that you can run at the same time. So in this scenario, what we will end up doing, we will end up creating this 10k of threads. right? So it's now, but normally the microservice instance that we the system resource that we choose for running a microservice happens to be in general a 4-core machine, which can handle a simultaneous of 8 threads. Now you can understand how much of load is coming to this particular machine. Okay, so 8 at a time, this machine can handle only 8 requests, right? But we have ended up creating 10k threads, so obviously this will crash, right? That's evident, we can't avoid it. Now initially we had an assumption that we will have only maximum one instance running for the service. Let's say now to handle this many requests, how many machines we require for this 100 millisecond time frame is like 10k divided by 8 instances we require. So it's like almost like roughly around 1000 instances. Right. So if we now do a cost analysis of this number of instances running simultaneously in say for example AWS, okay, or Azure, whatever cloud that the service that the organization may be using. So this will lead to huge cache amount or billing amount, huge billing amount. So what to do? So here comes the use case of reactive programming. Okay, so let me explain how reactive programming helps handle more requests in a microservice in efficient manner. Okay, let me first understand how conventional threaded request functions or works. Okay, say for example we have a series of tasks. Okay, say task 1 is like process the request. Okay, task 2 then query the database. Task 3, okay, receive the response from DB. Now task 4, process the response, and task 5, send out a final response to the client. Send the final response to client. Now this is a very generic stuff that happens on a request that is being sent out to a service. Now instead of querying a DB, it can be a query to cache, or maybe there may not be any DB involved. It may involve some file system. So instead of DB, it can be DB, it can be cache, it can be file system, where you have to read and write from a file. Okay, so we can do a lot of variety of thing with the as we get the request, right? Now if we analyze the utilization of the resource in this particular, say this whole task are being run by one single thread. Okay, this whole thing is being run in one single thread. Say let me give the name as th1 thread 1. Now analyze how all these tasks, that is task 1 to task 5, are getting executed in this particular thread. Let's draw a timeline. For example, let's say this is a timeline, okay, and starting from t equals to 0. So this is when the client sent request, okay. Client request is being sent out over here. At t equals to 1, we received the request, okay. Request received. At time equals to 2, we'll start with the first processing. What was that? So processing the request, as you can see. And so at time equals to 2, we started with task 1, okay. Task 1 started. At time equals to 3, we started with task 2. Say let's assume that each task takes 1 unit of time to get processed, okay. So at time equals to 2, we are executing task 1. At time equals to 3, we are executing task 2. So what is this task 2? Task 2 is querying the DB. Now here we need to take a deep dive. So when a request is being sent to this DB, say this is the DB, do we get the response immediately? Obviously not, because once the request has been intercepted by the DB has to query that internally and send a response. Say at time equals to 3, 4, 5 has been time 4 and 5 has been utilized to process the request at the DB end, and at time equals to 6 we got the response. So after getting the response, at time equals to 7 we'll proceed with task 3. So what is this task 3? Task 3 is receiving the response from DB, okay. So that is, we can make it at time equals to 3 only, we can call it as time t3, because at t3 we received the task. Fine. Now at time equals to 7, what we will do, we will proceed with the next task, that is task 4. So task 4 is, we are processing the response that we got from the DB, okay. So this is DB. And at time equals to 8, we will do the next task, that's task 5, that is we will send out a response to, is like sending response to client. So this is the you can say timeline of executing one request from the client, okay. So it takes 8 units of time. So UNIT, forget this one. So now observe one thing. Let's change the ink color for better understanding. Observe one thing. From time 3 to time 6, our thread is doing nothing. It's sitting idle. It's literally idle. Okay, it's doing nothing. So similarly, if, as we are seeing that if for 10k request, we will end up creating 10k threads, and for each thread, say if these are all the threads, for each thread we will have this block of time that is like this, which is like 3 unit of time, 3 UT of time, where our threads are sitting idle. So is this a optimized utilization of resource? Is this an optimized utilization of resource? Obviously the answer is no, okay, because our threads are waiting for something which it has got nothing to do with, because until and unless we get the response from a DB, our thread can't proceed with the other task. So here we are stuck. So for this scenario, reactive style of programming comes as a rescue. Let me explain how. In reactive programming, what happens? Every task are assumed or is being noted as event. So one task equals to one event. Okay. So we saw for a request we have 5 tasks. So it will be considered as 5 different events. In reactive programming, what happens? Say when we get a request, say request came in, okay, and as the request came in, we line up 5 different events, okay. So let's number it, and 1 minute. So as the request came, we have lined up 5 different events. So event 1, then event 2, then event 3, then event 4, and event 5. These are the 5 different events being lined up, okay. And here we have a concept of saying event loop. Okay, this is loop. Okay, so what happens? One event loop runs on one thread. So one event loop runs on one thread. Okay, so if say this is the thread, okay, this is a thread, and for one request we have these 5 events lined up. So first first event will get lined up over here. Once this is got executed, second event will come up, okay. Now if we remember, in the second event we were doing querying to the database, okay. So now since we send a request to DB, we have nothing more to do. We can proceed with the further tasks till we receive the response, as we discussed. So what will happen? So here, instead of waiting idle for 3 units of time, what it will do, for another request, say this is request 1, for second request also it will have 5 events lined up, right? So let's denote it with different color. So also this is first event, second event, third event, like that 5 events will be lined up, right? So what will happen here? The system is thinking, event loop is saying that, okay, I have sent a request to DB here, I have nothing much to do, I have to wait, so why not process other events? So here it will take up this first event of second request. It will also do process the second event of the second request. Now here also it did the same thing, it sent a request to DB. Now it's waiting. By the time now still we didn't get response from the first request because it requires 3 units of time. We have consumed 2 units over here. There is a first 1 unit, 2 unit. So here we can accommodate one more task. So what we can do, maybe for the third request also we have events to process, right? So what will happen here is we will process the first event of the third request. Say for third request also we have 1 events, like that 5 events are lined up. So we took up this first event, and then what can happen is that we may also process the second event of the third request, and then by that time we got the response from this DB, right? So what we will do, what this event loop will do is that it will now proceed with the third event of the first request. So got it. So our thread is no longer sitting idle for things to happen by the third party systems or maybe persistent systems over here. So we can process it third event of the first request, then fourth event, fifth event, okay, like that. And by that time we also got the response from the DB for the second request. So we can proceed like that. So what you can see is our thread is never idle. So we are always utilizing the time or the capability of a thread. So in this way, we can utilize the resource of the system more efficiently, and thus earlier probably for 10 requests we are probably using 10 different threads, but with this new concept or new approach we can process probably 3 requests in one thread, right? So it's not like that always 3 requests will get processed by one thread. Depends on the what is the intensity of the work or task that we are doing, but it's a rough estimation that always here in this reactive approach we are utilizing the resources in a more effective manner, and we are minimizing on the idle time of the thread, right? So this is the basic advantage of reactive programming over the conventional multi-threaded approach. So by reactive programming we are increasing the responsiveness of our microservices, okay, since after all we are utilizing the resources in a more efficient way than the conventional multi-threaded approach. So as the responsiveness of the service is increased, obviously it will impact the scalability of the service, okay, because we are naturally handling more requests in a more efficient way than the multi-threaded approach. And also reactive programming happens to be more resilient because they also give us the feature or the capability to handle the failure scenarios, okay. Therefore today we learned how reactive programming is more superior than the conventional ones. Please put down your comments or doubts in the comment section. I will try to reply to the doubts as soon as possible as I get time. And don't forget to like and subscribe. That will inspire me more to put more videos for you guys. And next we will look into the core Vertx feature as it is shown in a timeline. Let's see what the timeline is there. Okay, so we will deep dive into core Vertx features. Till then, take care and goodbye.